So today we are going to see the construction and operation of MOSFET. So the MOSFET belongs to the transistor family. These are some of the devices belongs to the transistor family. First one BJT, that is bipolar junction transistor. Second one MOSFET, metal oxide semiconductor field effect transistor. Next one static induction transistor, that is SIT. The next one IGBT, that is insulated gate bipolar junction transistor. So these are the transistor families. Today we are going to see only about the MOSFET. In previous class we have seen BJT. So the MOSFET metal oxide semiconductor field effect transistor is a combination of field effect concept and the MOS technology. So here this is the source and this is the drain. In between there will be some field. This will be induced. Due to that field there will be some channel is formed between the source and the drain, and the current will flows through this channel. And in gate layer we will have some metal oxide semiconductor, that is SiO2. So that layer will act as the dielectric, that is in capacitance we will have some dielectric, and there will be two metal plates on the both the sides, and in each of the plate there will be some accumulation of field or the charges. So same principle can be applied over here. There will be some metal oxide semiconductor layer, and there will be some positive accumulation of charges, and there will be some in the opposite side there will be some induced channel. Depends upon the type of MOSFET. If it is a P channel, the induced channel will consist of major holes, and if it is an N channel, the induced channel will consist of major electrons. And how the MOSFET is differ from BJT means, so the BJT is an unipolar device. The conduction is only due to the majority carriers, and the BJT is a bipolar device. So the conduction is due to majority and minority carriers, and the control signal used for MOSFET is an small control signal. Since it is an voltage control device, the MOSFET will require small control signal, and for BJT we will require large control signal since it is a current controlled device. So the control link will be it is a MOSFET is an voltage controlled device, and BJT is a current controlled device. And in MOSFET there are two different types of MOSFETs, that is depletion enhancement MOSFET, and the second one is enhancement MOSFET. So here the Q1 and Q2 are the enhancement MOSFETs, Q3 and Q4 are the depletion mode MOSFETs, and this is the constructional diagram for the depletion MOSFET. First one will be the depletion MOSFET, and second one will be the enhancement MOSFET. So here we can see the difference in the two symbols, that is if the line, and this first one is the gate terminal, and that is a gate metal terminal, and this line will be, it is discrete, means that indicates it is the enhancement mode or enhancement MOSFET. Since so the basic difference between the depletion MOSFET and enhancement MOSFET is there will not be any physical channel present in enhancement MOSFET. If the no channel is physically present in MOSFET between the drain and source layer, means that is called enhancement MOSFET. If there is some, if a layer is present, that is a channel is present between the drain and source layer, means that is called depletion MOSFET. So the depletion MOSFET can be operated in both the modes, that is enhancement and depletion mode, but the enhancement MOSFET can only be operated in the enhancement mode only. So here if this line is discrete, means so it is the symbol of enhancement MOSFET. If the line is continuous, means that is the depletion type of MOSFET. So that indicates, so there will be some physical channel between the drain and source, and if it is discrete line, means there will not be any channel between the drain and the source. And the arrow indicates the type of MOSFET, N channel or the P channel type of MOSFET. If the arrow is indicated inwards, it is N channel, and outwards means it is P channel. And this is the operation of N channel depletion enhancement MOSFET, and this is for the small signal MOSFET. So this is a drain, and this is the source, and in between, and these are the metal contacts. So we will have some three metal contacts: drain, gate, and source. And this is the p-type substrate, and we'll have some n layer for the drain and another n layer for the source. So it is a similar structure of an NPN transistor, and this is the n channel that is present between the drain and the source. And this is the SiO2 layer, that is a semiconductor silicon dioxide layer. And you have to give some voltage between the drain and source and gate and source. There we have to give the control signal for the gate and source, and main power source voltage is given across drain and source. So here this is the operation for this is the diagram for the n channel and the p channel. So the channel between the drain and source is n, that is the n layer, that is called n channel MOSFET, that will have p type substrate, and the drain and source layers are the n type layers, and the channel is also a n type channel, so that it is called as n channel MOSFET. And the substrate is n substrate, and the drain and source layers are p type layers, and the channel present is also the p type layer, that is called as p channel MOSFET. So this is symbol for the enhancement depletion enhancement MOSFET. Since the line is a continuous one, it indicates the physical channel is present between the drain and source. So the arrow indicates the inward direction of arrow indicates the n channel, and the outward direction of arrow indicates the p type channel. So this is the operation. So first one, we are giving the voltage across the for drain and source. We have to apply the power source or power voltage or the input voltage across drain and source, that is VDS is applied, and the gate source voltage is 0. So during that condition, so there will be some flow of current through this from that is positive terminal to negative terminal, that is a drain to source. The current will flow and the electrons will flow in the opposite direction. This is a conventional current flow direction, and the electrons will flow in the opposite direction to that of current. So when gate is equal to 0, or the gate voltage is equal, VG is equal to 0, so there will be some conduction and the current will flow from drain to source. And if VGS is negative, that if VGS is negative, means that mode is called a depletion mode, and if VGS, that is gate source voltage, is positive, means that mode is called enhancement mode. So here we have applied the drain to source voltage as positive to drain and negative to source, and we have applied the negative gate source voltage. VGS is negative and it is less than VGS off, that is called threshold voltage. So here we are having some we are applying the negative voltage to the gate, and it will induce negative charges or negative field over here, and in between we are having some dielectric, and in opposite side that will induce the charges of positive charges in the n channel. So if we are applying the negative voltage into the gate, means that will induce positive charges in the n channel, so that the width of the n channel layer is reduced, so the conduction will be reduced. So this will be indicated over here. So if we are going on increasing the negative voltage, then the more positive charges or more field is created in the n type channel, so that will reduce the conduction of this MOSFET. So when the gate voltage applied is negative, so that is called depletion mode, and when we are increasing the gate source voltage in the negative side, means so that will reduces the conduction. And this is the enhancement mode type of operation. So here we are applying the gate source voltage as positive. In addition to, we are applying the drain voltage as positive, drain source as positive, drain source voltage as positive. So for the gate voltage as positive, in enhancement mode, so if we are applying the positive, means so here the positive charges are accumulated in the outer layer, and in the channel, So that will induce more number of negative charges in the n-type channel. So already it is a n-type channel, and in addition we are applying the gate source voltage. Due to that, more number of negative charges are induced in this channel. So if more number of induced charges means, so that will increase the conduction. So in enhancement mode, if we are increasing the gate source voltage in positive, then the conduction will be increased. So in previous case, if you are increasing the gate source voltage in negative side, the conduction will be decreased. And in enhancement mode, if you are increasing the gate source voltage in positive side, then the conduction will increase. So this is the transfer output and output characteristics of n-channel depletion MOSFET. So here this is the center point, and the left to the region is depletion mode and right to the region is enhancement mode. And here we are having the VGS. The graph is drawn, the transfer characteristics is drawn between the VGS gate source voltage and the drain current. So VGS here for the enhancement mode it will be positive, and in for the depletion mode it will be negative. So if you are going on increasing the gate source voltage in negative side, so the conduction will goes on decreasing, and for a particular voltage of VGS, so the conduction will ceases or the conduction will stops, so that will become 0. So that is called VP, that is a pinch off voltage. And if you are increasing the gate source voltage in the reverse side, that is in positive side, the conduction will increases or it will enhances, so that is called enhancement mode. And this is the output characteristics. It is drawn between the VDS and ID, and for this we are having very low value of current, that is the off region or cutoff region. And this is the after this we are increasing the gate voltage in positive direction, the MOSFET will turns on, that is your active region similar to that of in BJT, and this is your ohmic region. And this is the enhancement MOSFET. So here we can see the difference. So in first slide we have we can see this, there will be some channel between the drain and the source, and in this diagram, so the physical channel is absent, that is there is no physical channel between the drain and the source. So if the gate, so as long as the gate source voltage is not applied, there will not be any channel and there will not be any conduction. If you are applying the gate source voltage means, so then only there will be some induced channel, so that will be responsible for the conduction. So this is the operation. So first one, it is an n-type n-channel enhancement MOSFET. So we are having the P substrate. So this is the two n-type layers for drain and source, and this is the gate. Three are the metal terminals, and in between the SiO2 layers. And here we are applying the voltage, that is VDD, that is drain to source, and here we are having the gate source voltage as positive. So if you are applying the gate source voltage as positive, so it will induce charges in this side as positive charges, and in opposite side there will be some negative charges, accumulation of negative charges, that is your induced channel. So due to this induced channel, the current will flows from the drain to source. So here if you are increasing the gate source voltage in positive means, so more accumulated charges will be in this channel, and the area of the channel will be increased, and hence the current conduction will be increased. So this is the symbol of the enhancement MOSFET, that is the discrete lines indicates the symbol of enhancement MOSFET, and arrow indicates the type, that is N channel and P-type. P-type channel MOSFET. It is inward direction means N channel, and it is outward direction means it is P channel MOSFET. And this also indicates the operation of enhancement, N channel enhancement MOSFET. So here applying the gate source voltage and positive charges are accumulated, and here more electrons are accumulated to create the N channel, and it will also repulse the holes, and more number of positive charges are repelled from this layer, and here more electrons, that is negative charges, are accumulated to create the induced channel. So this is characteristics of the N-channel enhancement MOSFET. So this the VT is the threshold voltage. So below which there is no conduction in the MOSFET. So the VT is the required gate source voltage, and if you are applying the gate source voltage beyond this threshold voltage, then the MOSFET will start the conduction. If it is less than VT means there will not be any conduction, the MOSFET will be in off state. So it is a minimum voltage to start the MOSFET for the conduction. And here we are having the cutoff region, and if you are increasing the gate source voltage beyond the threshold voltage VT, here you are taking it as 2 volt. If you are increasing the threshold gate source voltage beyond VT, that is 2 volt, the conduction will goes on increasing. For every increase in gate source voltage, there will be some increase in the drain current. So how it is happening means, if you are increasing the gate source voltage means the width of the channel is increased due to the increase in accumulation of the charges in that induced channel. So hence if the VGS is increased, the width of the channel is increased. So due to the increase in width of the channel, the drain current magnitude is also increasing. So it indicates if VGS is increasing, the ID will goes on increasing. And this is also the diagram for the P-type and P-channel enhancement type MOSFET. So in power MOSFETs, we will have most of the time we will use only the N-channel enhancement type MOSFET. Since we are using only for the switching operations, we will only use the N-channel enhancement type MOSFETs. So this is structure. What is the difference means? So here we will have some N-type substrate, and the drain and source layers are P-type layers, and here it will be P-type channel will be formed for this negative gate source voltage. So that is the only difference, but the operations are similar to that of enhancement, N-channel enhancement MOSFET. And these are the characteristics of depletion type MOSFET and enhancement type MOSFET. So in N channel, if VGS is increased beyond VT, then the conduction will increases and it will increases the drain current. And in P-type channel MOSFET, if VGS is greater than VT, then the current will be increased in negative direction. And here, this is the point, and here we are having two types of modes. Left to this axis, y axis is the depletion mode, and right to the y axis is the enhancement mode, and the same as that of here for the P-type channel. And this is also some of the characteristics, output characteristics of P-channel depletion MOSFET. So this indicates some similarity between the MOSFET and the MOSFET and the BJTs. So here this is the power MOSFET. So what is the difference between the power MOSFET and the small signal MOSFET means? So in power MOSFET we will have some vertical construction. Already I have explained what is the difference between the power devices and small signal devices. In small signal devices there will be some horizontal current flow, and in power type of devices we will have some vertical current flow. So what is the necessity for vertical current flow means, if you are enlarging the area to enlarge the area and to reduce the on-state resistance, we are going for the vertical type of construction. So here the drain is at one end and the source is at another end. The current flows in the vertical direction, that is from the lower side to the upper side through this layer. So here the vertical type of construction is adopted for the power type of MOSFET. So here we can see the N substrate. So here we can see that it is a similarity we can see. So for N channel we will have some P-type substrate and two N layers for drain and source. And in power MOSFET, so the majority will be P substrate. This is your P substrate, and the drain layers and the source layers are N-type layers. So here also the drain consists of two N layers, that is N plus N minus. N plus is the heavily doped N-type layer, and N minus is a lightly doped N minus layer. And these two layers consist of the drain type layers. So the drain consists of N plus and N minus, and the source layer consists of n plus layers, a heavily doped n layer, and in between we are having the p substrate, and the gate is also we are having some silicon SiO2 layer over here and metal contacts, and we are applying the drain to source, which drain is positive and source as negative, and we are applying the gate voltage as positive voltage, and positive to gate and so negative to source, so that will induce positive charges in this side, that is outer side, and in opposite side the channel is induced as negative channel. So this is the channel, and up to this it will be n type layer, that is n minus layer, and this is the small area in which the channel has to be formed. So the n type channel is formed in these two regions, and the current is flowing from this to in this direction to the source through this channel. If you are increasing the gate voltage, means the width of channel is further increased, and hence the conduction increases. So here also the current is flowing to this layer, and here the n minus layer will decides the voltage blocking capacity, that is, it is called drift layer, that decides the voltage blocking capacity of this device. So the MOSFET characteristics are already have been explained. So this is a circuit for this for plotting the MOSFET characteristics. So this is again the characteristics. So this is the transfer characteristics, and this is the output characteristics. So beyond if you are increasing the gate source voltage beyond the threshold voltage, the conduction starts and the drain current increases. And here we are defining the three regions: cutoff region, ohmic region, and saturation region. So cutoff region is related to the off state of the MOSFET, that is, there will not be any current or the minimum current, and this is the off state position of the MOSFET, and saturation region is the turn on position of the MOSFET, and this is the ohmic region. So it will not be operated. We are using the MOSFET in switching device, so the ohmic region it will not be operated. If it is operated in ohmic region, means it will be used in amplifier types, and here we are using only in cutoff region and saturation region. So for a lesser value of VGS, so the current will be minimum, and if the gate voltage is increased, means the conduction will increases, and the MOSFET will travel from the cutoff region through ohmic region to the saturation region. So for every increase in gate source voltage, there will be some increase in current, and after that in this saturation region the current will be constant, that is, irrespective of increase in VDS, the current will be constant. So that indicates the constant resistance, that is a constant on state resistance across the device in the saturation region. So the on state resistance plays major role in the switching operations, that is switching devices, since during the turn on condition of the device the on state resistance should be minimum. So as to minimize that resistance, we are going for the vertical arrangement of the MOSFET, and in saturation region we will have some flat curve, so that it is we can say that the on state resistance is constant. And this is also the diagram for the n channel power MOSFET, and this already explained, that is the construction and operation of this MOSFET. So these are the characteristics, that is n channel planar type or vertical type MOSFET, that is high power dissipation, that is planar type means horizontal type MOSFET, that is, it is high power dissipation due to large on state resistance, and feasible only for low power MOSFETs. And DMOS type, that is a diffused metal oxide semiconductor, and will have n minus drift layer that will decide the voltage blocking capability of the device. So this is the difference between the BJT and MOSFET. So BJT is a bipolar device, that is minority and majority carriers is responsible for the conduction, and it is the unipolar device, that is, it is a majority carrier device conduction. And BJT is a current control device. The input control signal is base current, that is current controlled device, and here we are applying the gate source voltage. It is a voltage controlled device, and BJT is negative temperature coefficient, and MOSFET is a positive temperature coefficient. So negative temperature coefficient means if temperature increases, the resistance decreases, and if the positive temperature means if the temperature increases, the resistance will increase. So that is called positive and negative temperature. So BJT cannot operate at high frequency. MOSFET is especially used for the high frequency operations, and the FBSOA, that is safe operating area for the BJT, is different shapes for the forward bias and reverse bias, and in MOSFET the safe operating area is similar for forward bias and reverse bias, and the secondary breakdown will not occurs in MOSFET, and secondary breakdown will takes place in the BJT. So that we can see in next class. So secondary breakdown is related to the, if the increase in temperature, so that will leads to breakdown of the device, and peak current capability is less than that of MOSFET. Here peak current capability of MOSFET is higher than that of the BJT. BJT is less sensitive to voltage spikes than MOSFET. MOSFETs are more sensitive to voltage spikes than BJT. The on-state voltage is lower than that of MOSFET, and therefore on-state losses are lower. The on-state voltage is higher than that of power BJT. So the on-state losses is higher when compared to BJT. On comparing on-state losses, BJT has less conduction loss or on-state loss, and when compared to MOSFET. So MOSFET will have some higher conduction or on-state loss when compared to BJT. Conduction losses of BJT are less than that of MOSFET. Conduction losses of MOSFET are greater than that of BJT. Switching losses are more in BJT, and switching losses are less in MOSFET. More energy efficient at low frequency, and it is more energy efficient at high frequency. So as conclusion, we can say that the BJT will have low on-state loss or conduction loss, and switching losses are more, and power MOSFET will have conduction losses of high value and less switching losses, and BJT is suitable for low frequency operation, and MOSFET is suitable for high frequency operation. Thank you.